Section 1.6, Handling Numbers. Having surveyed some of the units used in chemistry, we now turn to techniques for handling numbers associated with measurements, scientific notation, and significant figures. Scientific notation. Chemists often deal with numbers that are extremely large or extremely small. For example, in 1 gram of the element hydrogen, there are roughly 602.2 septillion hydrogen atoms. Each hydrogen atom has a mass of, oh my god, 1.66 times 10 to the minus, looks like about 25th grams. These numbers are cumbersome to handle, and it's easy to make mistakes when using them in arithmetic computations. Consider the following multiplication. Yuck. Look at all those zeros in front of it. It would be easy for us to miss one zero or add one more zero after the decimal point. Consequently, when working with very large and very small numbers, we use a system called scientific notation. Regardless of their magnitude, all numbers can be expressed in the form n times 10 to the little n, where n is a number between 1 and 10. Notice that's one of the rules for scientific notation. And the exponent is a positive or negative integer, whole number. Any number expressed in this way is said to be written in scientific notation. Suppose that we're given a certain number and asked to express it in scientific notation. Basically, this assignment calls for us to find n. We count the number of places that the decimal point must be moved to the given number to make it between 1 and 10. So it's kind of like, where do you draw the line to turn it into a number between 1 and 10, and then count the decimal places. If the decimal point has to be moved to the left, then n is a positive integer. If it has to be moved to the right, n is a negative integer. The following examples express this use of scientific notation. 568.762. Express it using scientific notation. Here's how I'd do it. I'd say, well, that's 5.68. Draw a line right there if you can see it. And then count the decimal places. I see 2, the 6 and the 8. So I'd say 5.68762 times 10 to the second, since there are 2 placeholders there. Note that the decimal point is moved to the left by 2 places and n equals 2. Here's another one. We've got 1, 2, 3, 4, 5, and then the number. But 7.72 should be a number between 1 and 10. Therefore, I'm going to do 7.72 times 10 to the minus 6th, since there are 5 plus the number in that section there to make it 7.72. It's moved to the right by 6 places, so n is minus 6. Notice that 10 to the minus 2, for example, is the same as 1 over 10 to the 2, which is 1/100th, which is 0.01, if you're wondering what these negative signs mean. Keep in mind the following 2 points. First, n equals 0 is used for numbers that are not expressed in scientific notation. For example, 74.6 times 10 to the 0 is improper scientific notation, but that would be 74.6 since, you're multiplying it by 1. Second, the usual practice is to omit the superscript when n equals 1. Thus, the scientific notation for 74.6 is 7.46 times 10, not times 10 to the 1, since that doesn't change it. Next, we consider how scientific notation is handled in arithmetic operations. Addition and subtraction. To add or subtract using scientific notation, we first write each quantity, say n1 and n2, with the same exponent. Then we can combine them so that the exponents remain the same. Now, it seems to me that this is a waste of time, since you can just calculate this. Perhaps this is an old-fashioned professor that wants to point some things out. 7.4 times 10 to the third plus 2.1 times 10 to the third would equal 9.5 times 10 to the third. Isn't that nice? 4.31 times 10 to the fourth plus 3.9 times 10 to the third can be re-expressed as 4.131 times 10 to the fourth plus 0.39 times 10 to the fourth, and then you can do it in your head. He's really showing you how to do these things in your head, which almost no young students today do, since the calculators do it for you. That's kind of very old-fashioned. Good for him. And he's going to do the same thing with multiplication and division. You can just multiply the early numbers. So 8 times 10 to the fourth times 5 times 10 to the second. I think he's going to, oh wow, look at that. Equals 40. You add the exponents, absolutely. So you multiply these two numbers, 8 and 5, that's 40. You add the exponents, that's 10 to the 6. 40 times 10 to the 6, that's 4 times 10 to the 7th. I'll save you the rest of the operations because, let's face it, most people are going to just punch them in. New topic, significant figures. Except when all the numbers involved are integers, for example, in counting the number of students in a class, obtaining the exact value of the quantity under investigation is often impossible. I think the other exact number is when you have something that's defined, like 12 inches equals 1 foot, for example. For this reason, it's important to indicate the margin of error in a measurement by clearly indicating the number of significant figures. Isn't that interesting? We're talking about margin of error. That's really what you're doing. And there's far more sophisticated methods to do margin of error, but this is a quickie. And so these are the meaningful digits in a measured or calculated quantity. When significant figures are used, the last digit is understood to be uncertain. For example, we might measure the volume of a given amount of liquid using a graduated cylinder with a scale that gives an uncertainty of 1 mil in the measurement. If the volume is found to be 6 mils, then the actual volume is either 5 or 7. So that means you're going to estimate a digit when you go ahead and calculate it. That's what makes the last digit uncertain. For greater accuracy, we might use a graduated cylinder that has finer divisions, so that the volume we measure is now uncertain by only 0.1 mil. This is assuming that that graduated cylinder gives accurate results, isn't it? If the volume of the liquid is now found to be 6.0 mils, we express it as being plus or minus 0.1. So it could be 5.9, it could be 6.1. Fine. And the actual value is somewhere between 5.9 and 6.1. We can further improve the measuring device and obtain more significant figures, but in every case the last digit is always uncertain. The amount of this uncertainty depends on the particular measuring device that we use. And then we have modern balances where they do the same thing. That last digit should be uncertain. Here are the guidelines for using significant figures. We must always be careful in scientific work to write the proper number of significant figures. In general, it's easy to determine how many significant figures a number has by following these rules. And notice there's 5 of them. Any digit that's not 0 is significant, so 1 has to be 1. I usually express this as, can it be written without it? And the answer is no, a number has to be included. Sometimes zeros can be dropped though. Thus, 845 centimeters has 3 significant figures. 1.234 kilograms has 4 significant figures, and so on. Rule 2, zeros between non-zero digits are significant. These are oftentimes called sandwiched or central zeros. Thus, 606 meters contains 3 significant figures. You can't say that number without including the 0. 40.501 kilograms contains 5 significant figures, and so on. Rule number 3, zeros to the left of the first non-zero digit are not significant. Wow, you probably have to read that about 4 times before you realize what they're talking about. This sounds to me like they're saying leading zeros you can dump. Their purpose is to indicate the placement of the decimal point. For example, 0.08 liters can be expressed as 8 times 10 to the minus 2 liters, and therefore those zeros are not there, so it only has 1 significant figure. And the other one would be all those zeros could be dropped. We only have 3 significant figures in 0.000349, and so on. If a number is greater than 1, then all the zeros written to the right of the decimal point count as significant figures. So that means you use, they usually say if that has a decimal place. So let's take a look. 2.0 milligrams. Now they usually just say trailing zeros. And this is trailing zeros are significant when you have a decimal place. So 2.0 milligrams has two significant figures. Reason, they measured it as 2.0, not 2.1, and they want you to know that zero's there, so it matters. 40.062 milliliters has five significant figures, and 3.040, all of those numbers, all four are significant. If its number is less than 1, then only the ones that are at the end of the decimal and the sandwiched ones are significant. Wow, they're really trying to make this sound complicated. It's just the leading zeros always dump, central zeros always keep, right side zeros, that means the trailing zeros keep. If there's a decimal place, it's not that bad. For numbers that do not contain decimal points, the trailing zeros are assumed to be insignificant. Perhaps you're counting by tens or hundreds. So 400 centimeter may have one significant figure, the digit 4. They might have been counting by hundreds, is how it's sometimes explained. We cannot know which is correct without more information. By using scientific notation, however, we avoid this ambiguity. In this particular case, we could say 4 times 10 to the 2, and that's clearly one significant figure. You could also say 4.0 times 10 to the 2 for two significant figures, etc. A second set of rules specifies how to handle them in calculations, at least simple calculations, as we'll see. Number 1. In addition and subtraction, the answer cannot have more digits to the right of the decimal point than either of the original numbers. Consider these examples. And once again, they're expressing it in a very complex way. And the way I would say it is keep the fewest number of decimal places. Do you see this number that they're using here, 89.332 plus 1.1 gives raw data of 90.432. But since 1.1 is only accurate to the 10th, we report it only to the 10th. And so we would say 90.4. If you have to round up, you round up. The rounding off procedure is as follows. To round off a number at a certain point, we simply drop the digits that follow if the first of them is less than 5. So what they're saying is if the final digit is 5, if the extra digit is 5 or more, you round up. Thus 8.724 can be rounded to 8.72 if you need to use only 3 significant figures. 8.727 could be 8.73, and 0.425 pounds, if you only want to use 2 significant figures, is 0.43, whatever those units are. Rule number 2. Got a different rule for multiplication and division. In this case, we keep the fewest number of significant figures. And here's how they express it. In multiplication and division, the number of significant figures in the final product or quotient is determined by the original number that has the smallest number of significant figures. That's exactly what I said. Of course, they said it in about 100 more words. The following example illustrates this rule. And 2.8 times 4.5039, the raw number is 12.61092, but 2.8 only has 2 significant figures, so we're simply going to say 13. Keep in mind that exact numbers attained from definitions such as 1 foot equals 12 inches, where 12 is an exact number, or by counting numbers, and they probably would say, hopefully in the problem that they're counting, can be considered to have an infinite number of significant figures. They then give a couple of examples for you to solve using this. The preceding round-off procedure applies to one-step calculations. If there's chain calculations, then you're always wondering what you should do with those intermediate numbers. That is, the calculations involving more one step. You get a different number depending on how you round off. I like the fact that they consider this. Most textbooks do not, and they have, I think, a very intelligent answer to this. This is one of the common things that just seems to go unanswered in most textbooks. Consider the following two-step calculation. A times B equals C, and then C times D equals E. What do you do with C? Let's suppose that A equals 3.66, B equals 8.45, and D equals 2.11. Depending on whether we round off all these off C to 3 methods or 4 significant figures, you get a slightly different number for E. Oh, you might get 2 different answers. However, if we had carried the calculation out as 3.66 times 8.45 times 2.1 on a calculator without rounding off the intermediate either answer, we would have obtained 65.3 as the answer for E. The point that they're trying to make in their usual long-winded fashion is to enter it all into your calculator and it'll automatically carry along lots of significant figures for you. Although retaining an additional digit past the number of significant figures for intermediate steps helps to eliminate errors from rounding, this procedure is not necessary for most calculations because the difference in the answers is quite small. So what they're saying is enter it all into one calculation